So yeah, first of all, let's look at this problem. When an electron moves from the electric field line, this A to B, along these lines, the electric field does some work, okay, some amount of work. What are the electric potential differences? VB minus VA, VC minus VA, and VC minus VB. Alright. So yeah, this is very simple one. But the main thing that we need to know is that when we are talking about equipotentials, and now these equipotentials mean that on every point on this line has the same potential, right? So that's why the equipotential. And whenever and always, and the other important fact is the electric field always is perpendicular. So this is always perpendicular to all these equipotentials, right? So this is a property of this electric field and the potential, right? So it is always perpendicular to this equipotential curves. So the questions are, what is the VB minus VA? So VB minus VA is just this one. So because they are lying on different potentials, so what we will do is we will just subtract VB from VA. So that will give us the potential difference between A and B. And this potential difference is given by the net amount of work done on this charge by the electric field divided by the Q. Right? So you plug in those values and you get some value. Right? Now the second question is, what is the difference between VC and VA? Yeah. So can you tell me, Ansh, what do you think? What should be the difference be between VC and VA? So what are you thinking? Can you think why what this should be?
The potential energy upon the charge.
Right. So what do we do? So will it be different? Will it depend on how whatever the distance is, this distance from A and C? It should
No.
not. It should not, right? Because this is the one equipotential. This is another equipotential. So the VC and VA, this difference is same as VB minus VA, right? So they are basically equipotential and there is no difference. So VB minus VA and VC minus VA, they are
Yes, sir.
same, right? And the last part is, what is this VC minus VB? And you see this B and C, they lie on the same equipotential. So the answer is 0. So there is no potential difference between this point C and B. Okay, yeah, simple enough. Right. Yeah, so there are some other simple problems. Yeah, so if you don't know, yeah, if I have not mentioned before, so these problems I have taken from the book. I think you might have heard. This is called so the authors are Halliday and Resnick.
Yes, sir. Halliday Resnick.
Yeah, so you have heard that. Do you read that book?
No, sir. Actually, in one H.C. Verma sir's course, he talk about that book.
Yeah. So this Halliday Resnick is very famous. It runs worldwide, right? And yeah, this has some serious hard problems. So the hardness of the problem is given by like these dots. So one dot means that this is simple enough, right? You can do it. This is simple enough. If you have two dots, that means that it is little bit hard. Okay, somebody else is joining. Let me just add him. Okay, yeah. Yeah, so if a problem has three dots, like we will do some three dots problem. So these are the hardest problem that you can get. So like if you want to do some really hard problems, you should solve all of these three dot problems in that Halliday Resnick book, and that will give you a very good idea and very good concept about what kind of problem you can have, and it will mainly brush up the
Sir,
core
what
concept.
does this go sign symbolize?
I think this Go means that if you buy this book, I think they will give you some access to their accounts. This Geo means this is probably there is some simulation available for this. I don't know. So there are some this kind of the symbols which tells you different things. So there will be sometime www. This tells that if you have some online account with this Wiley, with the publication, then you can probably find a solution there. Probably you can have some simulation, and you can have a tutorial on how to do that. So these kind of symbols are there. Yeah. So yeah, but the main thing is that we are considering, we are starting from a single dot problem to these three dot problems, which are supposed to be hardest, right? But also we are also trying to learn some of the tricks, so that we can just calculate this in very few number of lines. right? Because when you are writing for this entrance exam, you do not have a lot of time. You have to save each seconds. So each line saves a lot of time, right? So yeah, we will mainly try to focus on some shortcut tricks, or just eyeball these problems, how to eyeball and just do these things. Okay, yeah. So then let's move on to the next problem. Okay, yeah. So the electric field in a region of space has components Ey and Ex. So Ey and Ez is 0, right? Okay, so point A is on y axis, some coordinate, and point B is on x axis, also some coordinate is given. So what is the potential difference between Vb and Va? So here I have a rough drawing of the system. So yeah, so this is our point A and this is our point B, and throughout there is some electric field, right? In this space there is some electric field denoted by this 4x I had, there is no other component. Now to calculate this voltage difference or this potential difference between this A and B points, what we will have to do is we will have to calculate this integral, right? Now this dl denotes this is like dx I cap plus dy j cap plus dz k cap. But our electric field has only one component, that is the x cap. So this dl basically means that we have only Ex dx, right? This is the integrand that we will have to integrate. So what I have done here is I have just put in the points A and B. So A and B refers to these coordinates 0, 3 and 4, 0. So this is on y axis and this is on x axis. So you'll have to integrate this one, right? So you can directly integrate. This is a very simple one, but I'll show another trick that doesn't need integration. So that is, this is simple integration. You just know how to integrate this one. But for some complicated functions, you have a trick that you don't need to integrate. Okay. So for example, to demonstrate how that trick works, I am not initially integrating this. Okay. So what I am trying to do is I am trying to write this integrand, which is this 4x, in terms of an exact differential. Okay. So this kind of thing. So you see this dx square, and when I divide it by half, will give you x dx, right? So this dx square, half times dx square, is same as x dx, right? So what I am doing is I am writing this integrand in terms of an exact differential. So this is called exact differential. So yeah, there is this exact differential, and if we have exact differential and you have integration, then you can think that this integration is getting cancelled by this this exact differential, and you just plug in the value x square. Okay, I mean this is not the right way of thinking, but this will help you to remember this fact. So like this d and these integrations cancel each other. So d is the derivative, and integration is also called the antiderivative, right? So antiderivative and derivative, they supposedly cancel each other, and you get at the end of the day this x square. So no integration, right? So and you plug in the values. So you see, this is because just x square, there is no y, so I just plug in the x values. So I will plug in this 4 and I will square it up and I will get some number, right? So the main idea of this thing is, if you have some complicated field, like if you have some E dot dl, so E might have some different kind of components, some x, y, z, right? And you have been asked to calculate the potential difference between some A point and B point. And you might also have been asked to calculate this along some contours. Okay, so that means let's say I ask you to calculate the potential difference between the A and B along this path, or along this path, or along this path. But the fact is, this electric field is a conservative force, or it is a conservative field, right? So it doesn't depend on whichever path you choose. So the integration will always give you the same result. So it only depends on your terminal points, or your initial and starting point, right? So what we do here is, for this kind of thing, ex dx, ey dy, and ez dz, if you can find some function which is a function of x, y, and z, so that when you take a differential of this thing, you get back this this whole this integrand, right? So now if you can find that function, now you see again that this d and this integration will supposedly cancel each other, and you will have only f x, y, z with these limits b and a, right? Yeah, so this is b and a. and you just plug in those values, and you don't have to do any integration, right? Because sometimes these integrations can be real hard. So here the key point is, just remember that the calculation, this integration doesn't depend on the path. Whichever path you can take, you can take the simplest path and you can do this integration, or you can also avoid this integration if you can find an exact differential for your this integrand. Okay. Okay. So yeah. So is this clear, or you need to look at some examples? Is this clear? Can you get what I am trying to say? Okay, then yeah. Okay, so I'll take that as a yes. Yeah. So let's move on to the next problem, right? Yeah. So this is a little supposed to be a little hard. Okay. So a graph of the x component of the electric field as a function of x in a region of space is shown in this figure. Yeah, which I have enlarged here. The scale of the vertical axis is set by some value of this electric field, and the y and z components of the electric field are 0 in this region. Now, if the electric potential at the origin is 10 volt, what is the electric potential at x is equal to 2 meter? Okay, so just look at this first one. So 2 means this point. So what is the V at this point? So to calculate this V, the formula is what? B to A, that means VB minus VA, that is nothing but this integration, and at the end of the integration you will have to plug in those values A and B. And you see, this is because this electric field has only single component, only the x component. Then this is just the area under the curve, right? So this is just the area under the curve, and also you calculate the area under the curve, and you also plug a minus sign to get the potential. So what we will do here is, we will calculate the potential difference between this point x and point 0. Okay. So here you see this integration. So this E dot dl for this case is just this triangle, this triangular region, and you don't need to do integration. You can just, right, what is the area of the triangle. So that is the half times height and times the base. So that is the area of this triangle, and you already know the value of Ex, and this minus minus cancels, you get a plus, some plus results, and you already know the value of potential at origin. So just we take this thing and we just bring it to the right hand side, and then we calculate this Vx. Okay, so and that comes out to be 30. Yeah, you just put appropriate units. Okay. So yeah, so the second question is, what is the greatest positive value of the electric potential for points on the x axis for which this x is between 0 and 6 meters. Okay. So yeah, what is the largest positive value? So here you might notice a fact that whenever this electric field is negative, then only the potential will be positive, right? Because if the electric field is negative, then this minus sign will be cancelled and you will get a positive result for the potential, right? But here the electric fields are positive, so that means that this will give you some negative results for this potential, right? So because they are asking what is the greatest positive value of the electric field, that means we will have to just consider when the electric field is negative. And you see, the electric field is negative only between this 0 and 3, right? So if you just integrate, or you can, if you just find the area under this curve, you will obtain the maximum positive potential that you can have in this problem. So here again, this is a triangle. So the base is 3, so the height is just Exs, right? And this minus will be cancelled by this minus. And what else? Yeah, so the height is Exs and the base, and you just multiply it with the half. So this is what I have done here. So half, so there is one additional minus, half times this base times the height, which was minus Exs. So this minus minus cancel, right? And again we take this V naught and we just bring it to the RHS, and we have this potential. Okay, right? Simple enough, right? So yeah, so and the last part of the problem, for what value of x is the electric potential 0. So you see, we will have to find some x, right, which will lie probably somewhere here, right? So the potential becomes 0. Now the thing is, we only calculated the potential of this region from 0 to 3, which gave us some positive value, right? Some, I think it was 40, we calculated to be 40. So we will have to choose up to some x, so that it gives us some minus 40, and because the potentials add up, that means that when I will be sitting at this x, the total area will cancel, that means I will get 0 potential, right? So we will have to find this x, where this x lies. Now to do that, what I will do is I will calculate this area of this region only, of some, I'll choose some x, and I will try to determine what the x is, right? And because this region is, you can break this into two parts. So you have one triangle and you have one rectangle. So what we will do is we will find the area of the triangle and we will find the area of the rectangle, and we will just make it equal to this area of under this one, okay, and we will solve for x. So okay, in mathematical terms, so we have this triangle's area, right? Triangle's area is half times the height times the base, which is 1 in this case, and we have the area under this rectangular region, which is given by x minus 4 times this axis, right? And we will just put it to be 40, right? Because we want this thing to cancel the other half, the other negative in the e region, right? So we will just plug some values and we will just solve this thing. So this gives us x is equal to 5.5. So at something like x is equal to 5.5, around exactly here, so the net potential, so the areas will cancel each other, so the net potential at x will become 0, okay. Okay, so yeah, so let's move on to the next problem. So this is okay, this is a 3-star problem, supposedly the harder one, but yeah, let's see. So two uniformly charged infinite non-conducting planes are parallel to a yz plane and positioned at x is equal to minus 50 centimeter and x is equal to plus 50 centimeter. The charge densities are given by some numbers are given for these charge densities. I will just denote these charge densities by sigma 1 and sigma 2. What is the magnitude of the potential difference between the origin and the potential difference on this x is equal to plus 80 centimeter. So yeah, so the origin is exactly halfway between the sigma 1 and between these two plates. So this is the origin, and this is where we around here we will have some 80 centimeter. So yeah, I am denoting them by a and b, okay. So here I am also plugging the values of sigma 1 and sigma 2. Yeah, so there was no point of writing the sigma 1 sigma 2, yeah, my bad. But yeah, so the EA, so EA is around like here, right? So in the midway between these two plates. So what we will have here is, first of all we calculate these E's here, okay, E here, and you see because this is these are infinite non-conducting planes, so whenever you move inside this region, the electric field doesn't change. The electric field is always constant, which is a property of this infinite charge non-conducting planes. So yeah, so when you calculate EA, that means you have the whole knowledge about the electric field on all of these points, right? And also for EB, you can calculate this electric field and electric field. Yeah, so you just plug in the formulas, right? And you just keep in mind that there are directions for in this electric field, so there is this additional minus. Okay, at the end of the day, what we want to do is we want to calculate this integral which goes from a to b, right? So this, we break this integral into two regions. One is inside this two sheets and one is outside these sheets, right? So inside goes from 0.0 to 0.5 and the outside goes from 0.5 to 0.8, and for both of these regions we know exactly what is the electric field. So we can plug in the electric field's value, and at the end of the day we will obtain what is the voltage difference between this point and this point. Yeah, it was a rather simple one, right? Not that hard. Okay, yeah, so let's move on to the next one. Okay, yeah, so okay, what we have got here, so a non-conducting sphere has some radius, now some number, okay, and uniformly distributed charge q, some femtocoulomb. Take that electric potential at the sphere center to be V naught is equal to 0. What is V at the radial distance? R is equal to 1.45 centimeter. So see, you see this is already smaller than the radius. That means you are inside the sphere. and the second part is what is the potential at exactly on the surface at r is equal to r. So first of all, let's calculate that r is equal to this point. So I am denoting the point by this a. Okay. So what we will do is we will just plug in the electric fields, which is just, as you know from Coulomb's law, this is dq by r square, right? And because you are inside a sphere, then this dq is nothing but, so this is rho times dv, right, not sigma. So this is rho times dv, and dv is given by 4 pi r square times dr. Okay, so we will plug all of this. So we will plug rho times 4 pi r square. There is some cancellation, 4 pi gets cancelled, r square gets cancelled, right? And at the end of the day, we will have to do this integration on this dr. So integration of dr will just give us some r, so, right? So you can plug in the r is equal to this 1 point whatever that number was, 1.45 centimeter, and you can obtain the result, the number, right? So what I have done here is I have plugged the original q. So what is the relation between the rho and q? So rho is the uniform charge density, right? So we divide the whole q by just volume, 4 by 3 pi r cube. So I have just plugged in that formula, and yeah, I have kept it like that. Now we can also plug in r is equal to r into this equation. So r is equal to r, we will cancel one of these r's, and you see that this value, this doesn't depend on any variable r, right? So that means you can plug in any r is equal to 2r, 3r, or r is equal to anything, right? It always, this outside this sphere, the potential always remains constant. So to just tell you the whole story in a single diagram, that means, so look at this diagram. So this is the potential, and this is how we are changing the radius, right? So as we are changing the radius, at the origin the potential was 0, right? It was given in the problem. So at the origin the potential was 0, right? And we calculated the value inside the sphere, and we saw that it increases linearly. So yeah, this is a straight line passing through the origin, and as soon as we cross the value of this, as soon as we cross the surface, which is r is equal to r, then we see that it becomes constant, right? So this is a simple way to describe how the potential is throughout for the various r's. Okay, yeah, okay. So let's move on to the next problem. Yeah. So this is an interesting problem. I like this problem. A spherical drop of water carrying some charge has potential of 500 volts. Okay, 500 V. Okay, at its surface, so V is equal to 0 at infinity. Right. So what is the radius of the drop? Okay. So yeah, interesting enough. So the potential of a some sphere, as we have seen before, is given by V by 4 pi. So V is equal to Q by 4 pi epsilon 0 r. But this r is the radius of the sphere, right? So this is the radius of the sphere. So what we will do is we will just solve for this r. So you get the V down here on the right hand side, and plug in all of the values. So you obtain the radius. Okay, you get some value, right? Yeah. So the second problem is, if two such drops of the same charge and radius combine to form a single spherical drop, what is the potential at the surface of the new drop? Okay. Yeah, so this diagram is not, so this is from the other problem. So yeah, it was there. Okay, so if we have two drops, similar drops, right? So first of all, we will have to determine what is the radius of the drop, right, of the resultant drop. So you see, if we just merge these two drops of the same volume, then what we will get is the a drop which is twice the volume, right? And from this kind of equation, we can find the radius of the new drop. So which is like, so we add up the radius of the original two drops, which is just 4 by 3 pi r cube and 4 by 3 pi r cube, and we equate it to the radius of the volume of the new drop, which is given by the 4 pi by 3 pi r prime cube. So this is the r prime. So we will solve for r prime. So it is something like 2 to the power 1/3 times r. Okay. So we have obtained the radius, and we also know that the charge also add up, right? So the charge from this and this will add up and will give us 60 picocoulomb. So yeah, so here we have 2q, and we have plugged in our value for the r prime, which is 2 to the power 1/3 and r times r. Okay. So this is the potential, right? So yeah, you plug in the values and you just obtain what is the potential of this net of this new drop, right? Okay. Yeah, yeah. So this is a very, yeah, this is conceptually important problem, and this might seem a long problem, but this is yeah, this is one line or two line problem. Okay. So yeah, this shows a rectangular array of charged particles fixed in place with distance. So a is equal to 39. So each of these a means 39 centimeter. And the charges shown in are shown as integer multiplies of q1 is equal to 3.4 and q2 is equal to 6 picocoulomb with v is equal to 0 at infinity. What is the net electric potential at the rectangle center? Okay, so there is a hint which tells us thoughtful examination of the arrangement can reduce the calculations. So the main interesting thing is to work with the potential is a scalar quantity. It is not a vector, and you can add them, right? You don't have to consider the directions and all. So first of all, we have to calculate the potential here. But first we note what our charge distribution is. So we see that this charge, so this charge and this charge are in the same distance, right? Same distance from the point, and this charge and this charge are also in the same distance. So as if like they lie on some circle, right? Some imaginary circle, okay? And if they are lying on a circle and they are equidistant, then you can just add them up and you can pretend there was a single charge, okay? So if I just add all these charges on this same radius, then what do you get? So there is minus 3q and minus q, that gives us minus 4 times q1, and also there is plus 2q1 and plus 2q1, that gives us plus 4q1. So the net charge is 0, right?
0.
Yeah, exactly, Ansh. So that means these charges will not contribute. The potential will be 0 because the charge is 0, right? The potential for all these 4 charges will be 0. So only the contribution, the non-vanishing charge. So you see there is 4q and there is 4q, right, which is equidistant from here, but they don't cancel. They give you 8q2, right? They give you 8q2. So for only these 2 charges, you will have some potential, right? So for these 2 charges, we will plug in our this potentials form, and we know the distance was a by 2. Yeah, this distance was a by 2, right? So that is what we have plugged in, and this is how we obtain the potential, right? Yeah, very simple, very simple. And yeah, I have written all this stuff, but you see, you could have done this just by eyeballing it. You don't have to write anything. Okay, so yeah, so similarly, so there is some other charge distribution. Yeah, don't look at this one. This is some other problems part. Okay, so what is the net electric field at point P due to the 4 particles if v is equal to 0 at infinity? Okay, so yeah, we are being asked to calculate the potential at here at this P point. Okay, so what we can do is first of all, we'll again look at this this equidistance particle, right? So this plus q, minus q and plus q, so the resultant will be just plus q, right? So for this part, we will consider only this q by d, right? So this is the only single charge that contributes to the potential, right? So net charge, right? And this one with minus q also contributes, but the distance is different, so minus q by 2d. So again, you just do it in a single line calculation, and this is supposed to be a little hard one, but yeah, you can do it with just a single line. So yeah, you get some resultant one, and if you want, you can go ahead and plug in the numbers. Okay, yeah, very simple ones. Yeah, so okay, let's move on to the next one. Okay, so in this figure with the charges q1 and q2, these are fixed in place with a separation d, with electric potential defined to be v is equal to 0 at infinity. What are the finite positive and negative values of x at which the net x electric potential on the x axis is 0, right? So in this quadrant, what is the x where the v is 0, and in this quadrant, what is the x where this potential is 0. Okay, so first of all, let's analyze where it can be. So there are basically 3 regions. One is the negative half, right, x less than 0. One is this in between region between 0 and d, and one is the region like here, which goes beyond this d. Okay, so here, because this q, okay, so because this q2 is negative, and when we will be going away from this point, we will mostly see the charges of q, we will mostly see the potential of this q2 charge, right, because this is the closest to this point. So in this region the potential will be negative, so we can't hope that we might have some point where the potential can be 0, right. So the only choice can be that we can have some points in between, so that the positive potential and negative potential cancel each other and give us a net 0, right. Now to solve that, I will assume that okay, there is some x point, and I will write this potential, the net potential at this x point, and I will make it 0, and I will solve for the x. So yeah, so there are some initial 4 pi epsilon 0 factors which we don't need, right. So I have only written this q by r and this q1 by x and q2 by d minus x, this part. Okay, so this is x, this is the distance, and this distance is d minus x, right. So yeah, this is the two contributions coming from this q1 and q2 at this point x, and what we will do is we will just solve for x. So if you solve for x properly, you will see that you will get a point, neutral point we will call it, where the potential is 0, which is just d by 4. It is a quarter of this d distance. Okay, so this is the positive value where the this potential vanishes, right. So they have also asked to find a negative value of this x. So what we will do here, similarly we will assume that there is some x, right, some negative x, and we will just write the potential there also, right. So here we have written, so q, so this is x distance, and this distance from this q2 is x plus d. So you just plug those two values and you will solve for x. So we see that the d, so the x is d by 2, right. So here, so the main thing was we have to just eyeball one region out, so that we can work in two regions. So I eyeballed it out because the q2 is higher in charge, so higher in magnitude than q1. So in all of this region we will have a negative potential, we cannot have any 0. But you see q1 is smaller than q2, right. So there can be some x that can balance out and give you some 0 points. So that was the whole idea. Okay, yeah, so I think I will be able to do a last problem. Yeah, so this is a very interesting problem. Yeah, it's supposed to be simple one, and this is the problem about a continuous distribution. Okay, so these are two configurations, right. So one configuration has only positive charge along this rod, and another configuration has half positive and half negative. Okay, so I think this part is given in most of the books, so how to calculate this one, but anyway I will just repeat that. So what we will do is, for that problem we will assume that there is a dq element, okay, and this dq element gives rise to dv potential, and so we also have this r, and r we can calculate, this is just by Pythagoras theorem, this is just x square plus d square square root, and okay, so now we will have to integrate over these small potentials, and this integration will go from minus L to plus L, right. And as you know, so this function here, the integrand is an even function, right. So we will just get 1 2 outside, and we will make this integration from 0 to L, and as you know, this integration will give you just log, right, log from 0 to L. So you just plug the value of log and you can have this, right. So this is a little bit tedious calculation, but for the second half of the problem, so this might seem a little bit more tedious, right, because half of this has some charge and half of this has exactly different charge, signs are different, right. But the thing is, first of all, we again look back at some element dq, right. So here I have jumped couple of steps, but I think you can write the potential. So this potential is again integration over minus L to plus L, but here the catch is the lambda here, the charge, linear charge density, is not a constant anymore, it is a sine function. So for region, it is like a minus of sine function. So for like when x is greater than 0, then you have negative charges, right. So you know sine function, right. So sine functions, sine means this is, yeah, not this one, is gn. So sine function of any negative number, so any negative number will give you minus 1, sine function of any positive number will give you plus 1. So this lambda is just like sine functions times some magnitude lambda naught, which is given in the problem. So when you get the sine functions, these sine functions makes this whole integral an odd function. So you see where I am going with this. So odd function will make sure that when you are integrating over minus L to plus L is symmetrical opposite limit, then this will make sure this becomes 0. So you don't even have to do this integration, right? You can just identify, okay, the lambda becomes an odd function and the integration will vanish. So